When you watch a high-speed physical impact, our human perception registers the chaos as a single fluid event. Metal warps, energy dissipates, and structures collapse in a continuous flow of physical destruction. But inside a finite element analysis environment, a computer does not experience this event as a stream of motion. The software cannot process the fluid nature of a real-world crash. To solve the physics, the solver relies on time discretization. It slices the event into millions of isolated, frozen fractions of a millisecond, known as time steps. At each of these frozen intervals, the software ignores the past and the future. It evaluates the state of equilibrium only for that specific infinitesimal moment. Governing every one of these intervals is a single mathematical engine, the dynamic equation of motion. To understand how software predicts material failure, we have to deconstruct this equation and map the strict chronological loop that an explicit solver uses to step a simulation forward. Computational collision analysis functions as a relentless, discrete numerical time-marching process. This is the baseline dynamic equation that must be satisfied at any given time step. Inertial forces plus internal forces must equal external forces plus contact forces. The M represents the global mass matrix, the distribution of mass across every node in the entire system. A U is the nodal acceleration vector. Together, M A U represents the inertial forces that resist any change in motion. Fn is the internal force vector. This maps the material's structural stiffness and internal damping, the resistance the metal provides as it deforms. On the right side of the equal sign, Fx represents the external applied loads acting on the system from the outside environment. Finally, F contact is the vector representing collision forces, the resistance generated when two separate meshes attempt to occupy the same space. In this mathematical framework, a physical collision is treated as a force vector acting on the nodes, rather than a rigid boundary constraint. Before any movement occurs, this equation must perfectly balance the internal resistance of the material against the external loads of the impact. Traditional implicit solvers attempt to solve directly for final displacement, requiring the solution of massive systems of simultaneous equations. The explicit method changes this approach. Instead of solving for displacement, we manipulate the algebra to isolate the nodal acceleration, W. First, we shift the internal forces to the opposite side of the equation. This groups all force vectors together on the right. Next, we isolate acceleration by moving the mass matrix to the right side, where it becomes an inverse matrix. This is the finalized explicit equation. Acceleration equals the inverse of the mass multiplied by the net force acting on the system. The term inside the parentheses is the net force acting on the vehicle at that exact microsecond. By multiplying this net force by the inverse of the mass matrix, the solver computes acceleration for every node without solving simultaneous equations. This algebraic shift focuses the solver exclusively on the rate of change in velocity at the current moment, rather than the final position of the mesh. Once the explicit equation yields the acceleration for every node, how does the computer actually move the 3D model? It follows a rigid kinematic update cycle to advance the simulation in time. Step 1 calculates net force. In Step 2, this force yields nodal acceleration. Step 3 integrates acceleration to find velocity. In Step 4, velocity is integrated to calculate spatial displacement. The solver then updates node coordinates, and the clock advances to repeat the cycle. The physical geometry of the mesh moves only at the end of this mathematical cascade. Force determines acceleration, which yields velocity, which dictates displacement. Explicit collision analysis involves the repetition of this four-step cycle millions of times per second. The loop executes successfully only if every input force in the equation is known at the start of the step. This creates a specific challenge for the F contact vector. The solver lacks geometric awareness to identify when parts occupy the same space. Without instructions, the meshes simply clip through each other. If the solver does not recognize that a collision is occurring, F contact remains zero, the meshes penetrate, and the simulation loses physical validity. To maintain the loop, the solver must generate a repulsive contact force the moment meshes begin to overlap. This requires specialized algorithms that bridge the gap between abstract matrices and physical boundaries. Calculating F contact is the necessary transition into the final layer of crash dynamics, the penalty method.